Okay, so we're back, and you may notice this heading here. We'll get to what that means in a second. But underneath it, you'll see a statement that I've found through years of teaching calculus. So we've spent several videos now talking about different ways to evaluate the limit of a function as we get close to a point. Some of the different tricks we end up having to invoke. But without fail, pretty much every student's favorite way to evaluate a limit that I've ever seen is this guy right here, what we referred to as the direct substitution property previously. That we just take our limiting x value, plug it into the function, and see what we get. That's generally just about everybody's like, yeah, that's like your first move. Try to plug in the limiting x value. If you get a result, awesome. It's only when something fails that you have a problem. This is one of those things students like so much that sometimes I have a hard time getting people to do other things. Like, if this doesn't return a number, they immediately assume the limit doesn't exist, in spite of multiple examples we've done as we work through section 1.3, where, no, getting like a zero denominator doesn't automatically mean the limit fails to exist, and we'll see more examples of that as we go on here. But anyway, so this direct substitution property is pretty awesome. It's in fact so awesome that it gets its own name. So, if it turns out this is true, we have a special name for it. You might already be able to guess that special name. So, we say if that direct substitution property holds for a given c value, f of x is continuous at the value c. Sorry, my head's in the way there. So yeah, that. And as it turns out, an awful lot of what we do in calculus really kind of builds on this notion of continuity. So f of x is continuous, at a given point. We will also talk about a function being continuous on like an interval. In that instance, it really means we're continuous at each point in the interval. Continuity is sort of by its nature a very, very local property. You look at it point by point. But if we say it's true for a whole set of points, then it's true for each one of them individually. In particular, I've often found kind of a useful visual interpretation of a function being continuous comes back to its graph. So if we have a function that's continuous on an interval, I don't know, I'll call it a to b. So the idea is once I start drawing my graph here at a, I can draw the graph over the entire interval without ever having to pick up my marker. Like if I do this and then I have to stop and jump somewhere else, or that's kind of a key that we're not continuous at that point in question. So so this is a graph of a function that is continuous on this entire interval from a to b. All right. So as it turns out, you might start wondering, well, do we know under what circumstances a function is continuous? Like the functions we know and love already, like trig functions and exponentials and polynomials and whatnot. Where are they continuous? Good news. They're pretty much continuous anywhere they're defined. We're not going to drag you through all of the the proofs. That's for a different class. But for now, the functions we know and love, if they're defined at a given coordinate, it turns out they're also continuous there in most instances. We'll see a couple of edge cases as we roll on here, but that ends up giving us sort of a useful tool because we kind of already know how to track down where a function is defined. You've done that before, like in a pre-calculus class. You had to identify the domain of a particular function. So if you're comfortable with tracking down a function's domain, you're also pretty good at tracking down where a function is continuous. So let's take a look at some examples and see how this goes. All right, so first example here, we've got what you might call an algebraic function. We've got a linear thing here sitting underneath the square root. The square root of x plus 7. We want to know for what x values this thing is continuous. I tend to abbreviate continuous with CONT, so if you see that, that's what it means. So we want to know where this thing is continuous. I've already kind of let the cat out of the bag. This is going to be continuous for any x value we can meaningfully plug into this and get a real number result back. So hopefully you recall square roots, even roots in general, fourth, sixth roots, what have you. If something like this pops up, we can't have something negative underneath the radical. That's like a complex or imaginary number, and that's bad as far as like Calc 1 is concerned. It has value outside of this course, but for now, you can just roll with that. So we need to keep the stuff that's underneath here from being negative. So we need x plus 7 to be greater than or equal to 0, or x is greater than or equal to negative 7 if we do a little algebraic razzmatazz to it. Now, we haven't had to play around with this an awful lot yet at this point in the course, but generally speaking, instead of talking in terms of inequalities like this, we tend to like to represent places where the sets of values where a function is continuous using what we call interval notation. So you should be familiar with that, but so in interval notation, we need everything that's bigger than or equal to negative 7. So negative 7 off to infinity and beyond. Since we want to include this, we have that or equal to. Hopefully you'll recall that if we want to include an endpoint of an interval like this, we use a squared off bracket to indicate that. For what it's worth, remember, infinity's not a number that we're like doing arithmetic with, so yeah, there's like never a squared off bracket here for the purposes of Math 115. So that's our domain slash set of continuous x values in this instance. So that's one example. Let's take a look at another. Okay, a little bit more involved here. We have the natural log function. So we didn't talk a lot about domains and ranges before, but you may recall that the natural log function, we can't have anything negative in here, kind of like what we saw with the root function just a minute ago. Additionally, the natural log of 0 is undefined as well, so there's no power we can raise something to raise e2 to get 0. So anyway, so we have to have x being greater than 0 here. So x greater than 0, or in interval notation, that would look like 0 to infinity. So I kind of wish I'd put in like a negative here. If it had been negative x, then we actually need explicitly negative numbers, and then we would have from negative infinity running up to 0. Note the parentheses here because we don't want to include 0 in this instance. I also feel like maybe I should apologize a bit because if it turns out these are both like real numbers, like this has been 0, 5 or something like that, it can be kind of tough to distinguish between an open interval and like an ordered pair. Generally, I think context will tell you which one you're dealing with, but do be on guard about that. But yeah, interval notation is generally how we want to take a look at things like this. All right, another one coming up. All right, this guy's a polynomial. He's probably the nicest of the bunch that we've seen yet. It's just a plain old quadratic. X squared minus x minus 12. So again, if you're sort of trying to track this thing down in terms of a domain to figure out where it's continuous, well, there's no x value. We can't plug into that and get a meaningful result back in turn. So for all real numbers x, if you want to get more specific, I'm short on space, so I just said for all, just for all x. If we were writing that in interval notation, it would look like the following: negative infinity to infinity. For what it's worth, if you're doing this sort of thing in web work, I believe instead of the classic sideways 8 for infinity, web work will ask you to type in, I think it's like capital INF for infinity in those instances. So don't worry about looking for like a fancy symbol to put in. The homework problems generally kind of guide you on the formatting you're expecting. All right, so I want to do one last modification of this guy, and then we'll move on and talk about some other stuff. Big change, huh? Yeah, so same polynomial is living up in the top of this expression. I've now just kind of put x plus 3 underneath it. So if you're trying to figure out what's going on here, again, tracking down domains, we can't have negative stuff under radicals. The other big no-no, hopefully you'll recall, is dividing by 0. So we can't let the thing in the bottom of this fraction end up being 0. That's means we need to avoid an x-coordinate of negative 3. So in interval notation, what's this going to end up looking like? So we have everything up until we get to negative 3. and then open the parentheses, or close off these parentheses rather. We don't want to bracket parentheses because we don't want to include it. Then on the other side, we have -3 to infinity. Conventionally, I know like WebWork will ask you to do this. I put this little symbol we call a union symbol in here. So I think in WebWork it's just like a capital U connecting your sets. So that's how I would represent that. So this is where it is continuous. So now, as it turns out, points like this are actually kind of important to us for other reasons. So we're going to call points where it turns out continuity fails, where the function value is not equal to the limiting value. We're going to call those points of discontinuity. I know how big my handwriting is. I don't think I can fit that word in there. So we have a point of discontinuity at x equals -3, or I'll also usually, I told you I wasn't going to be able to fit it. My handwriting is large. So I usually would just refer to x equals -3 as a discontinuity in the function, or to say that h of x has a discontinuity at x equals -3. Some textbooks will use the term, they'll say that h of x is discontinuous at -3. I tend to avoid that. I like saying has a discontinuity. But so that's sort of the idea here. All right. So I want to take a look at some more examples, but time's drawing short on what I can record in a single video. So we'll probably pick up with the same example next time, and then kind of do like a compare and contrast thing with another case where it turns out a function's not continuous everywhere. So have fun.